Right, good day everyone. We're carrying on with a bit of trig consolidation. I'm sure some of you freaked out in the last lesson, but you're going to be absolutely fine. If you don't understand what's going on at the end of this lesson, yeah, phone Mrs. Garofoli at any time. She's waiting for your call. You should have your notes for session. At this stage, actually, you should have no notes in front of you. All I want you to do is listen to this video, then you're going to go back and complete your worksheet by yourself, and then you're going to mark it. And helping out to give us advice today is Jasmine. Hello, Jasmine. Thanks for coming in. And actually, Jasmine's just been sitting on Francis. I'm sorry, Francis. I hope you're okay. Thanks, Francis, though. Jasmine, don't bully her. And we have Kai as well. Okay, coming through to help us. Thank you, guys. Right. So first of all, I gave you a little bit of homework from last week. So let's just share that screen. Okay. All right. And the homework was you're given a diagram on the Cartesian plane. Okay. X, that's 0 degrees, that's 90 degrees. You're given the point 41. You're given some angle beta. Remember, your angles are measured in an anti-clockwise direction on the Cartesian plane. That'll be 0, 90, 180, 270. Okay, right. And the question said go find tan beta, sine beta, and cos beta. Now, first of all, remember the stupid poem. Okay, shade your rear, which tells us that sine for a specific angle is the ratio of the y-coordinate over the radius. Cos x raised, so cos is the ratio of the x-coordinate over the radius for an angle, and shade your rear because x raised tan your exterior, which tells us that tan is the ratio of the y-coordinate over the x-coordinate. So to work out tan beta, we've got no problems. Tan beta is the ratio of the y-coordinate over the x-coordinate, which in this case is simply going to be equal to 1 over 4. That's the ratio of tan beta. So tan beta is 1 over 4. Sine beta, though, is the ratio of shade your rear. Sine is y over r, the y-coordinate over the radius. The problem is we've got the x-coordinate, we've got the y-coordinate, we don't have the radius, which is the distance from the center to the point. But remember that r squared is always equal to x squared plus y squared, okay, from Pythagoras. And so r squared in this case is going to be 4 squared plus 1 squared. So r squared is 17. So your radius, we leave in third form. Your radius is root 17. So now I've got x, y, and r. Okay, so sine beta is equal to y over r. So sine beta is your y-coordinate is 1, and your radius is root 17. So it's 1 over root 17. And then last, cos beta, well, cos is equal to the x-coordinate over the radius. Okay, and the x-coordinate for this angle beta is 4, and the radius is root 17. So your answer is going to be, because cos is x over r, so cos beta is equal to 4 over root 17. All right. Then, okay, now it says given sine 30 is equal to a half. Again, you're not going to be asked a question like this in an AP exam. It's just about trying to get your understanding of trig, okay, in your head, clear in your head what this trig is all about on the Cartesian plane. Okay, just when you in core, you'll also do trig in triangles. Okay, you'll start off with that and then you'll move into Cartesian planes. So it's just about getting a bit of a head start in trigonometry. So it says given sine 30 is equal to a half. So they give you that statement. Okay, you can check on your calculator. Remember, to work out sine of 30, you go, if you're given the angle, you go sine 30. If you're looking for the angle, you go sine to the negative 1. So sine of 30 degrees, and you see it's equal to a half. Right. So it says illustrate the above statement on the Cartesian plane. Make use of a minimum of 3 points. Right. So Jasmine, what's the definition of sine? Shade your rear. So sine, they're telling us or the calculator's told us, that sine of 30 is equal to half. What is that telling you? It's on the Cartesian plane. It's telling you that if you draw at an angle of 30 degrees for any point on that line, okay, that then the ratio of the y-coordinate over the radius is equal to 1 over 2. So if you measured an angle of 30 degrees, well, this is just a guess, okay, so sine of 30 degrees, we measure an angle, I'm going to extend that line quite far. There's an angle of 30 degrees, okay, just an estimate of 30 degrees. And they tell us that the y-coordinate over the y-coordinate, if the y-coordinate is 1, the radius is 2. So in other words, if I went 1 up, so if I put a point over here, and doesn't tell us anything about, we could work out the x-coordinate, but for now I just want you to understand what this is saying to you. It's saying that if the y-coordinate is 1 at this point, the distance to get to that point, in other words, the radius, is equal to 2. Right. So that's one point that illustrates that sine of 30. Remember, sine of 30 is equal to a half. Sine is just a name for the ratio of the y-coordinate over the radius. But for what angle? If you change the size of the angle, the ratios would change. Okay. Right. So that's what that's telling us over there. But they asked us to use 3 points to illustrate that sine of 30 is equal to a half. Well, how the hell can I use 3 points? Well, it's a ratio, right? So what's half the same thing as? There's a million different points we could use, but we could say, okay, it's the same thing. A half is the same thing as 2 over 4. So this was a half over here in pink. Okay, 2 over 4. Well, what's that saying to us? If sine of 30 is equal to a half, sine of 30 could also be 2 over 4. It's the same thing. Sine of 30 is equal to 2 over 4 is the same thing as sine is equal to a half. So what's that saying to you? If you went 2 up, okay, instead of 1 up, you went 2 up, okay, then for 30 degrees, if the y-coordinate was 2, because the ratio is a half, then this distance over here, the radius there, would be equal to 4. That's also illustrating the fact that sine of 30 is 2 over 4. Sine of 30 is 1 over 2. They're the same thing. Those ratios are staying fixed. Sine is a ratio of y over r. And if I make up one more, okay, I'm just going to pick any number. We could have 10 over 20. Obviously, I'm not in scale now. What's that telling us? That if we went 10 up on an angle of 30 degrees, if we went 10 up on an angle of 30 degrees, then it's guaranteed. If you, in other words, if your y-coordinate was 10, it's guaranteed, okay, that the distance to get to that point, okay, must be equal to, because the ratio is a half, that radius must be equal to 20. Okay, so those are 3 points, 1, 2, and 3. All 3 of them are illustrating that sine 30 is equal to half, that the y-coordinate over the radius is equal to a half. Okay, not just for 1 over 2, it could be 2 over 4, 10 over 20, 1,000 over 2,000, a million over 2 million, but for 30 degrees, that ratio is staying fixed. Lovely stuff. Right. Then, whoa, example 2. Okay, so Kai. It says given tan 45 is equal to, and then there's a space. So it's not a mistake. Okay, I want you to go to your calculator and go work out what tan 45 is. And if you go tan of 45, you get an answer of 1. Well, what does that mean? Okay, well, we know that tan is equal to the y-coordinate over the x-coordinate, right? It's a ratio for a specific angle. It's the ratio of the y-coordinate over the x-coordinate. So what this is telling you is that tan of 45 is equal to 1. 1 just means 1 over 1. Right. So how do I go illustrate that? Well, it's saying for an angle of 45, the y-coordinate and the x-coordinate must be the same. Okay, that's all it's saying to you. So if I went and illustrated it, 45 kind of chops that in half. So 45 is somewhere over here. I'm illustrating tan 45 is equal to 1. So if I use the numbers 1 and 1, that would illustrate that point. If x is 1, y is 1. and then tan 45 is 1 over 1. So tan 45 is equal to 1 is telling you that for an angle of 45 degrees, if I divide the y-coordinate by the x-coordinate, I get an answer of 1. Is that the only point? Well, okay, that illustrates that. However, well, I could have 2 over 2. If I gave you this point over here, 2 across, 2 up, it's also telling you that tan of 45, if I just gave you that, and I said to you, what's tan of 45, and I gave you that point, you'd say tan of 45 is 2 over 2, which simplifies to 1. Okay, and likewise, I could have, not to scale, 1,000 and 1,000. So those are 3 points which illustrate the fact that tan of 45 is equal to 1. Okay, what is trig about? Trig is just the names of ratios. And on the Cartesian planes, it's the ratios, the comparisons. Okay, the fact that the ratios stay fixed for the x-coordinates, y-coordinates, and the radius of any point on the line that forms that angle. Okay, hope you're getting an intuitive feel of what trig's about. Okay. All right. Example 3 says, given cos theta is equal to root 3 over 2. So they don't give us the size of the angle now, right? So it then says, illustrate the above on the Cartesian plane using the given ratio. So we don't know the size of the angle, but Francis, what do we know cos is the ratio of? Good, cos is the ratio of the x-coordinate over the radius. So we don't know where that angle is. Okay. If you get that size of the angle wrong, it doesn't really matter. But we've got something like this. Okay. And we don't know the size of the angle, so I'm just going to call the angle theta. Okay. But we do know if I pick a point on this line, okay, and if I let the x-coordinate be root 3, then the radius must be equal to 2. If the x-coordinate is root 3, for this angle, cos of theta, the ratio of the x-coordinate of the radius is root 3 over 2, right? So now, okay, first question, I've answered that first question. Well done, Francis. I've illustrated the above on the Cartesian plane using the given ratio. That's all I can do at the moment. Then it says, without using a calculator, evaluate tan theta and cos theta. So Jasmine says, right, I know that tan theta is the ratio for this angle theta of the y-coordinate over the x-coordinate for any point on that line. And I've got the x-coordinate to 3, and I've got the radius is 2. Okay, in order to figure out tan, I need the y-coordinate that goes with it. So you start off with our standard thing, which links up x, y, and r, which comes from Pythagoras, is that x squared plus y squared is equal to r squared. I'm looking for y. What's the y-coordinate? So y squared is going to be equal to r squared minus x squared. So if I plug in the numbers, in this case, y squared is going to be 2 squared minus root 3 squared. So y squared is equal to 4. Root 3 squared is just 3, so it's going to be 4 minus 3. So y squared is equal to 1. So y could be plus or minus 1, but I can see the y-coordinate is positive. So the y-coordinate is 1. So I could fill in now that the y-coordinate is equal to 1 over there, right? Okay, the x-coordinate is root 3, and the radius is 2. So for this angle, this particular angle theta, okay, we don't know the size of it. Okay, tan is the ratio of the y-coordinate over the x-coordinate. So the y-coordinate is 1. Okay, the x-coordinate is root 3. So tan theta is equal to 1 over root 3. Okay, right. The next question says, go evaluate cos theta. Well, cos theta is the ratio of, that's a dumb question. Sorry, go change the question. That should be sine theta. We've got cos theta. Okay, apologies. Okay, so sine theta. Now you can write a strongly worded email. Okay, sine theta is the ratio of the y-coordinate over the radius. What is the y-coordinate? Okay, the y-coordinate is 1. So sine theta is equal to 1 over the radius, which is equal to 2. So I get sine theta is equal to a half for that particular angle. Okay, and remember, if I extended it, I could have 2 and 4. I've extended all before. Okay, those ratios anywhere along those lines will be the same. Tan will be 1 over root 3. If I'm here, it'll simplify to that. So up here, sine would simplify to 1 over 2. Those ratios stay fixed, right? Okay, and last question, so that was question B. Just A over here. And question C says, go find the use your calculator to determine theta. So I could use any of these ratios. I could use tan theta is equal to 1 over root 3. I could use sine theta is equal to a half. Or I could use the original cos theta is equal to root 3 over 2 to find the angle. So let's use tan, okay? Because we're often going to use tan. So I know that for this angle, tan theta is equal to y over x, which was 1 over root 3. So to find an angle, I go, remember to look for an angle, I go shift tan to the negative 1 of 1 over square root of 3. Okay, and I should get an answer of 30 degrees, and it is. So we've worked out that this angle theta is equal to 30 degrees. Okay, right. So in other words, if actually that angle is 30 degrees, and then those ratios would be that over there, and those ratios would stay fixed for an angle of 30 degrees. Right, so you're doing very well. Okay, example 4. Okay, given this point 4,1. Okay, we didn't do one like this before, did I? Ah, shite, I did it. Excuse me. Okay. Exactly the same question as before. I was just making them up. Okay, so good news is, okay, yep, you can skip example 4. All right, that was quick. Okay, so leave it at that. Okay, variety. Okay, if I now go do, let's just make up one question. So I gave you this. Oh, no, you all squeal. Okay, you've got enough. And as I say, you're not getting tested directly on Trig. Okay, make sure you understand the ones we did very carefully. Right. Okay, page 6, Argand diagrams. Okay. So remember, a complex number can be written as z is equal to a plus bi. For example, z is equal to 2 plus 3i, or something like that, right? Any complex number, it's got a this, remember, is called your real component, and the 3 is your imaginary component. Okay, so any complex number can be made up of a real part and an imaginary part. And any complex number can be illustrated as an Argand diagram. And an Argand diagram is drawn on the complex plane. Now, in the Cartesian plane, so it says any complex number can be represented on the complex or Argand plane. The complex plane or the Argand plane, instead of calling this the x-axis, sometimes they do call it the x-axis, but I always label it like this. You've got the real part of the complex number is illustrated over here, and the imaginary part is illustrated over here. So what the hell are we talking about? So I'm just going to go straight to some examples, and it says represent the following, okay, as an Argand diagram. So just move it down a little bit, refocus it. Okay, so it says represent the following. Okay, we're given that diagram over here. This is the complex plane or the Argand plane, and it says represent the following as Argand diagrams. So number 1, you've got the complex number z is equal to 4 plus 2i. Well, the point I'm going to label then is, well, the real part is kind of like the old x coordinate, is going to be 4 and 2, okay, and the imaginary part is the y coordinate. So the point z, 4, 2, okay, it means we go 4 across and 2 up. So some books label this just z, 4, 2, and sometimes they label it z. It means the same thing as z is equal to 4 plus 2i. So that point, okay, if you get just given a point over here, the point Z42, what does that mean? If it's in the Cartesian plane, it means this is the complex number 4 plus 2i. Okay, so it's not on this thing here, but I'm going to make up one. If I said to you, you've got the point negative 2, 2. So say I gave you this point over here. I called this complex number A. And I said to you, A is the point negative 2, 2. What complex number does that represent? Okay. Well, Jasmine says that represents a complex number. A is equal to negative 2 plus, I'm filming, plus 2i. So I don't think I'm in. So A is equal to negative 2 plus 2i. And I can't pause it. Sorry, Brogues. You can borrow some of my stuff. Okay. Right. A is, no, but they can see you, China. So A is equal to negative 2 plus 2i. Okay. So I've got that over there. Sorry. Oh, dear. Sorry about that. Okay. That is that complex number. Negative 2 plus 2i would be illustrated by that point A negative 2, 2. Means I've gone negative 2, the real component is negative 2, and the vertical component is positive 2. Okay. Right. Then the next one. Okay. You've got, if I illustrated this, x is equal to minus 3 plus I. Well, what's the point? I would, if I want to illustrate, represent that complex number on the Argand diagram, x would be negative 3, okay, and the y coordinate, the real part, the imaginary part is 1. So negative 3, 1 would be over here, and that is the point x. So x is negative 3, 1. It's pretty easy. Okay, so I've done that one, I've done that one. Number 3, now p is equal to negative 1. Well, that means the same thing as p is equal to negative 1 plus naught I. I know it's a bit lame to put in the naught. So what does that mean? Well, the real part, the x coordinate is negative 1, and the y coordinate is 0. So if we get some color in the matter here, x was over here. Okay, z was illustrated over there. Okay, and p negative 1 naught is going to be over there. That's the point p negative 1, 0. Okay, right. Then the next one, q is equal to negative 2i. Okay, that means the same thing as q is equal to naught plus naught minus 2i. So the real component is 0, and the imaginary component is negative 2. Where's that going to be? Naught negative 2 is over there, right? So that is the point, complex number q on the Cartesian plane. And then m is equal to negative I plus 3. Be careful, I've written that deliberately the wrong way around. So the real part, I could write that as 3 minus I. So the real part is 3, and the imaginary part is negative 1. So I've got 3 negative 1, and 3 negative 1 is 3 across, negative 1 down. It's over here. So this is the point m 3 negative 1. Okay, right. And last of all, this point t negative 3 minus 3i. What we're going to label? Well, the real component is negative 3, so that's the x coordinate. The y coordinate would also be negative 3. So t negative 3, 3 would go negative 3 across, negative 3 down. There's the point t negative 3, negative 3. Okay, right. So that is simply how we illustrate points on the complex plane, how we illustrate complex numbers on the complex plane, or we call those Argand diagrams. Okay, complex numbers on the complex plane, or complex numbers on the Argand plane, same thing. Right. Okay, that makes some kind of sense. Okay, so if the last thing, if I said to you, this is the point 2 negative 3, Jasmine, what's that point? And the point would be, if I call this, I don't know, r, r would be representing the complex number 2 minus 3i. Okay, I hope that all makes sense. Right. Okay, getting there now. Okay, the next thing says, it's a fancy word, the modulus of a complex number z, once again, z is something like a plus bi, or in other words, z is equal to 7 minus 3i. Okay, the modulus of a complex number z is the distance of z from the origin. It's basically what we call the radius on the Cartesian plane. Okay, the radius on the Cartesian plane, it's the same thing, the distance from the center to the point, okay, on the Cartesian plane. So the notation that we use for the modulus of a complex number z is two straight lines around it either side. So the modulus of z we write as mod z. We read it as mod z. Later on you'll see we also read that as the absolute value of z. We won't use that notation for now. And then the argument of a complex number z is the angle between the real axis and the line joining z to the origin. So what the hell are we talking about? Okay, well, if I gave you a diagram over here, sorry, the argument of z, the notation is we simply write the argument of z. Okay, so the argument of a complex number z is the angle between the real axis and the line joining z to the origin. That's a fancy way. Okay, so the argument of z, well, if I have some complex number and there is z, right, then the distance from here to here, okay, we're going to call mod z. That is mod z, whatever that distance is. It's a distance, right? That is the modulus of z, the distance from here to here. That was your old r on the Cartesian plane. And then this angle, okay, in an anti-clockwise direction from the positive x-axis, okay, that angle over there is what we refer to as the argument of z. Okay, so the argument of z is that angle, the same kind of angle we worked with in trig, but now we're just using different language. So the different language is what we used to call our radius, we now call mod z, and what we just labeled some angle theta, we now call the argument of z. So the argument of a number is an angle, the modulus, okay, is so that's an angle, okay, that's the angle to the point, that's the distance from the center to the point, okay, from the origin to the point. So if I gave you this question over here, given z is equal to 1 plus I, calculate mod z and the argument of z. Any question like this, where they ask you to calculate that, always draw the Argand diagram of the complex number. So, what's I can't always draw the Argand diagram of the complex number. So you've got z is equal to 1 plus I. Okay, what's the point we're going to illustrate? Well, the real part is 1, so I'll go 1 to the right, and I'll go, the imaginary coefficient is 1 as well. So I'm going to just plot the point, 1, 1. So it's a rough sketch, 1 across, 1 up. My real part over here, I've got my imaginary part over here. So now I've got the point 1, 1. Okay, I can draw this in. Okay, the distance from here to here, from the origin to the point, so this is the point z1, 1. That distance here is mod z. Okay, right, and this angle over here is the argument of z. Often we just label it as theta like we did in trig. So this is the argument of, that's what they mean by the argument of z, that's the modulus of z. And from all the trig we've been doing, what's the relationship between these things? X squared plus y squared is equal to r squared, right? So in other words, okay, the modulus of z squared is equal to x squared. You can start off with write x squared plus y squared is equal to r squared. You're not going to be penalized. So the mod z squared is going to be equal to 1 squared plus 1 squared. Okay. So in other words, mod z is equal to 2. So the modulus of z is going to be the square root of 2. So there's the modulus of z. Okay. And then to find the argument, well, I've got my old x and y coordinates, right? And as I say, you're not going to be penalized if you use that notation. Okay, and I'm going to just label this angle theta like we did in trig. So I can say, right, I know that x coordinate and a y coordinate, right? And I'm going to try to find angle theta. So I know what links up x and y. Well, tan of theta is the relationship between the y coordinate and the x coordinate. You could use r if you wanted to, but you're given y and x, so we may as well use that. So tan of theta is going to be equal to 1 over 1. So tan theta is equal to 1. And if I use my calculator, we actually did this earlier on, and we go shift tan to the negative 1 of 1, I get an angle of 45 degrees. So theta is equal to 45 degrees. You can leave it like that, or you can say the argument of z is equal to 45 degrees. So to answer the question, okay, if z is equal to 1 plus I, illustrate always, first step, draw the Argand diagram, right? Once you've drawn the Argand diagram, you kind of can visualize what's going on. You've got the point 1, 1. To find that distance, it's just x squared plus y squared. So mod z is 1 squared plus 1 squared, which is root 2. To find the angle, you'll always be given the x and y, so you may as well use tan. Tan is equal to the y coordinate over the x coordinate, so tan is 1. How do you use your calculator? Shift tan to the negative 1 of 1, and you get 45 degrees. So the argument of z is 45 degrees. Right. Last question. Okay. Question 8. Okay. Given z is equal to 3 plus I, determine mod z and argument of z. Right. Always draw a diagram first. So if I draw my diagram, okay, I'm going to have, what's the point? This is my real component. This is my imaginary component. The point I'm working with is, the real part is 3. That's how much I've got to go across. The coefficient of I is 1. So I've got to plot the point 3, 1. Just a rough sketch. I've gone 3 across and 1 up. So here is z. It's the point 3, 1. Or you can label z is equal to 3 plus I, either or. Okay. As long as you've got your real part and your imaginary part. Draw up your line from your origin to that. I'm going to call the argument of z, I'm just going to give it a label theta, okay, and this is mod z over there, that distance from the origin to the point. Okay, so for this complex number, what's the modulus of z? Well, z squared is equal to x squared plus y squared, which is 3 squared. You can start off with r squared is equal to x squared plus y squared if you want. So z squared is equal to 3 squared plus 1 squared. So mod z squared is going to be equal to 9 plus 1 is 10. So mod z is equal to root 10. Okay. And then to find the argument, well, I've always given the y coordinate and the x coordinate. Okay. And the ratio of the y coordinate over the x coordinate is called, given the name tan. So tan theta in this case is, the y coordinate is 1. The x coordinate is 3. So tan theta is equal to 1 over 3. To find the angle, I go shift tan to the negative 1 of 1 divided by 3 equals, and you get, and I split it to 2 decimal places. So theta is equal to 18. That's an angle, so don't forget your degree sign. So your theta is equal to 18,43 degrees. So in other words, if you illustrate theta there, you get all. If you want, though, you can write argument of z is equal to 18,43 degrees. Right. Now it's up to you. Okay. If you want to consolidate this, go print out the worksheet, the blank worksheet. Try to complete it yourself. That'll give you, that's the best way to do things, to get a proper understanding of things. Okay. The memo is up there. After you've done that, the memo is on Teams, and you can go mark your worksheet. You don't have to go watch the whole video again. Okay. It's up to you. If you understand it and you think you got it waxed, well, then you don't have to do any of that really, I guess. Okay. Go off and have a pina colada. All right. I thank you to our 3 guests again, to Jasmine, Kai, and Francis. Your support is greatly appreciated. Arrivederci. Ciao.